Up to this point, we've worked under real numbers where we can't really square root a negative value. Now we're going to consider a case that we can square root -1, for instance, and that's going to be defined as the value I, where this is called the imaginary unit. Sometimes they call it non-real more or less nowadays because imaginary sounds like we're making this up as we go along, and that's really not the case. It's just that now with doing the square root of a negative, you're actually going into a fourth dimension, and we live in a three-dimensional world, so it becomes hard to envision this. So under this condition, if you were asked to do the square root of -4, you could actually split that up and say, well, I'm going to have the square root of -1 times the square root of 4. The square root of -1, of course, would be I, because that's how we're defining it. Square root of 4, of course, is 2, and we would say that the square root of -4 is 2I. This is a non-real answer. This was not going to show up on a graph or anything because graphs only deal with real numbers. However, we can actually now do this and come up with an answer. Well, one of the first things we look at when we deal with this imaginary unit I is, well, what can happen with various operations involving this? So first off, if I just have the imaginary unit I, which equals the square root of -1, what if I were to square this? Well, if I square I, that's like taking -1 square rooted and then squaring. Well, if I square a square root, all that happens is those two operations cancel. I'm left with -1. So I squared is -1, which is a real number. So I can square an imaginary number and end up with a real number. If I were to take I to the third power, that's like having I squared times I. Well, I squared we just defined as -1. -1 times I would be -I. I to the fourth, well, that's just taking I squared and squaring that. And I squared, of course, is -1. And if I square a -1, I get 1. The reason why these are done is because if I just take various powers of I, these four values are going to repeat. Because if I do I to the fifth, I can write that as I to the fourth times I to the fourth is just 1, and I would get I again, starting back here. I to the sixth, very similar. I would have I to the fourth times I squared, which is 1 times -1, which equals -1. I to the seventh would be I to the fourth times I cubed, which will eventually work out to be -I. I to the eighth would equal I to the fourth squared, which is 1 squared, which is still 1. So this pattern of I, -1, -I, 1 keeps repeating as I keep raising this to various higher powers. So basically, there's only four values that raising I to a power can possibly have. That being said, if I was asked to do something like I to the 57th power, well, all I have to do is realize, well, which one of those four values is this going to be? And the way to do that is simply take the exponent and divide it by 4. And when I do that, I get 14 and the remainder of 1. Well, it's really the remainder that's going to be the most important part, and I'm going to explain why, because this means I have 14 I to the fourth, so I have I to the fourth to the 14th power times I to the first power, the remainder. All of this is just going to become 1, because I to the fourth is 1, 1 to the 14th would just be 1 again. So you would be left with I. So I to the 57th power is just going to be I. I to the 122nd power, for instance, doesn't matter how big these get, all you have to do is take this and divide it by 4, and you would get, in this case, 30.5. It's not the quotient part, it's the remainder part that's important, because notice the remainder part became the new power of I to the first here. Here, because I'm getting a 0.5, means I have 31.5, which means that I had a remainder of basically 2 out of 4 when I did this. And so the remainder was 2, which means that This is the same thing as I squared, and I squared is equal to -1. So this would just equal -1. So basically, you're just using this idea here and these first four values, and then you're going to just divide the exponent by 4 to figure out if it's going to be equal to I to the first, I to the second, I to the third, or I to the fourth, which are I, -1, -I, and 1 respectively. So you divide the exponent by 4. If you get a number with 0.25 following the decimal point, this is assuming that you're doing this on the calculator, which most of you probably would, at least for the time being. That means you get a remainder of 1. It means it's going to equal I. If you get some number 0.5, that means you had a remainder of 2. That means that that's going to equal -1. If I get some number times 0.75 when I divide the exponent by 4, it means I had a remainder of 3. That's going to equal -I, because that's what I cubed was. And if I just get some number with no remainder, that's going to equal 1. Complex numbers in general are a combination of real numbers and imaginary numbers. So they always have this form a plus bi, where a is the real part, bi is the imaginary part. When you add or subtract complex numbers, you combine like terms. That's all it is. So if I take the two numbers 4 plus 6i and 7 minus 3i, these are two complex numbers. They just have two parts to them. So this is a single number, single complex number, the 4 plus 6i. This is a single complex number. Well, all I have to do for this, because I'm adding, I don't really need the parentheses. I'm just going to combine like terms. I'm going to do the 4 plus the 7. Those are the real parts. I get 11. The 6i minus 3i is going to give me a positive 3i. So 11 plus 3i would be the result of adding those two numbers together. When I subtract them, however, I have to be a little bit more cautious. It's a very similar process. I can drop the parentheses on this, but this negative needs to be distributed. So this can be dropped. For me to drop the parentheses here, I have to change the sign of both of these. So I'm going to have that -1 distributed, and I'm going to have a minus 7 plus 3i. Now I combine the like terms. 4 minus 7 is going to be -3. 6i plus 3i is going to be a plus 9i. So when I have 4 plus 6i minus 7 minus 3i, I get -3 plus 9i as a result. When I multiply two complex numbers, I have to remember to FOIL. So if I'm multiplying 4 plus 6i and 7 minus 3i, I have to first FOIL this out. So I'm going to do 4 times 7 and get 28. 4 times -3i and get a -12i or a minus 12i. 6i times 7 is going to be a plus 42i. And a 6i times a -3i is a -18i squared. Now, complex numbers are a closed system. That means if I perform any operations with them, I should end up with a complex number, which all of them can be written in this format. Having this I squared does complicate things a little bit, but from what we talked about powers of I squared is the same thing as -1. So this actually became the real number when I multiplied those two pieces together. And so what I have here is 28 minus 12i plus 42i plus 18, because I had minus 18 times -1. That's going to become a plus. 28 plus 18, those are the two real parts, is going to give me 46. -12i plus 42i is going to give me a plus 30i. So the overall solution to that multiplication is 46 plus 30i. It works the same way when I take a complex number and raise it to a power. And most of the time, you're just going to be asked to square it. I have to keep in mind that that's the same thing as 4 plus 6i times 4 plus 6i. I'm going to FOIL this again. And if I do that, I'm going to end up with 16 plus 24i plus 24i plus 36i squared. Of course, adding a 36i squared is the same thing as adding a 36 times -1, which makes this a minus 36. And so when I combine my like terms, I'm going to have 16 minus 36, which is negative 20. 24i plus 24i is 48i. So that's an introduction to how to perform the various operations you'll be asked to do with complex numbers. In this course, you're not asked to do division of them because that's a complicated circumstance, and this course doesn't ask you to do it, whereas the other college algebra class does. So it's just making sure you know powers of I. You know how to add complex numbers, subtract complex numbers, multiply complex numbers, including raising them to powers. And so that's what the following examples are going to have you do. For the time being, this is the end of this video. If you have any additional questions, please make sure to bring them up during class.